So before solving this differential equation, I want to do a couple examples on finding the boundary conditions. So in the first example, we're going to find the boundary conditions as defined here, the initial current. So note here the notation is 0 plus. So plus is that moment right after the switching event happens. Recall that from chapter 7. Which equals the moment right before, because there cannot be an instantaneous change. Here it's important, and we'll see later why we annotated as 0 plus. So we're going to find the initial current through the inductor, the initial voltage of the capacitor, the first derivative of the current. We need to know the rate of change that current is initially changing, in other words, as well as the rate of change at which the voltage across the capacitor is changing. And then we need the final values for both the current and the voltage. Okay, and our example is given as follows. So we have a capacitor and an inductor and a couple resistors, and we have a switch that is across this 10 ohm resistor, such that when the switch is closed, we're shorting that 10 ohm resistor. When it's open, the 10 ohm resistor is in the problem. And we're going to find, and the current is defined here through the inductor, and the voltage is defined across this capacitor. So we're going to assume, just like in chapter 7, that this switch has been open long enough such that steady state applies. It's important. Assume steady state applies at t equals 0 minus. So first we're going to take the case where t equals 0 minus, assuming, again, that we're in steady state conditions. We're going to redraw this circuit. So note that when we're in steady state, since we only have a DC source, the capacitor looks like an open circuit. The switch is open, so the 10 ohm resistor is there. The inductor looks like a short circuit, and that's connected to the 24 volt source. So this is I0 minus, which also equals I0 plus, because the moment that the switch closes, it will be a different circuit, but they must be equal to one another because we can't have instantaneous changes. And V0 minus is going to equal V0 plus. Okay, so now we just need to solve this circuit for V and I. So noting that the 10 ohm resistor is just in series with the 2 ohm resistor, we can find the current pretty quickly is just being defined as 24 volts divided by the entire series path of resistance, which is 12 ohms. So initial current is 2 amps. And we can find the initial capacitor voltage V0 plus as being the voltage dropped across the 2 ohm resistor. So it's a voltage divider of the 2 ohm over the entire path, 2 over 12. So that works out to be 4 volts.